test 3 should end with what we do tonight. Whatever I finish by, whatever I finish by 8:05 tonight is going to be the official end of test 3's material. And I'm hoping it's going to be polar double integrals. So any questions about the test? What I'd like to do, I think I mentioned on Tuesday night, start putting the test in the testing center on Saturday and then giving till next week. I'd like for you to take some time to kind of absorb the homework, I guess. And what if I just put the test in the testing center Monday and leave it in there through Saturday of next week?
Wow. Hey, that would be...
Okay. And that gave me an extra day to make it out. So I mean, in all honesty, there probably won't be too many of you took it on Monday or Tuesday of next week. You probably want to take advantage of an extra contact hour on Tuesday night to iron up any kinks that you may have. So I'll be in here early and I can stay late if you have any questions, and then try to get the test done by the end of that week. Yes, sir.
Awesome T-shirt, by the way. But next week is going to be all test 4 material.
Next week is all test 3 material.
Oh, it's still all test 3 material.
Yeah.
Oh, so we're not even...
Oh, so what we're going to be doing in class, you mean? Oh, we're going to be yes, we'll be starting test 4 material in class on Tuesday and Thursday of next week.
So
yes.
whatever we cover tonight is on the test, and then everything else is on the test.
So I'm kind of, if you go to the calendar that I gave you a couple of weeks ago, I'm essentially taking the double integrals and polar topic here and moving it to tonight, and taking the remainder information on triple integrals that we really haven't had a chance to start yet, and moving it to there. So I'm just swapping those two topics. And then all of next week, Tuesday and Thursday of next week, is all about triple integrals. We're doing XYZ, triple integrals and XYZ rectangular coordinates on Tuesday night. And then I'm introducing you to another couple of coordinate systems. We're doing polar coordinates tonight. And just a quick show of hands, who has seen or used the polar coordinate system at some point in the past?
In pre-cal.
In pre-cal. See, and that's rare. 1730, every once in a while, depending on the semester, some teachers get a chance to teach it, some teachers don't, because it's actually not, it's not a big requirement in pre-calculus. Well, I think it should be, because I think you should see polar coordinates before getting into Calc 3, because it hits you like a brick wall sometimes when you see it for the first time this late. But so it's going to be new to most of you. I need to introduce you to what polar coordinates are before we go into the double integrals. But then all of next week is going to be devoted to triple integration. I'm doing XYZ rectangular coordinates here, and then doing the cylindrical spherical coordinate systems there. Okay. Any questions? So I'll put the test in the testing center Monday-ish, okay, maybe Tuesday, and then leave it in there through Saturday of next week. Would that be okay? Any potential conflicts with that? All right. Any potential conflicts out there, email me and let me know. Okay. So before I actually go into, you probably have the notes on double integrals and polar coordinates. I need to do something better than just a rudimentary introduction to the polar coordinate system. Have you ever used graph paper like this?
Unit circle?
Well, it looks unit circle-ish. Some people are going to start breaking into the Spider-Man theme song if you look at it long enough, because it does kind of resemble a spider web. But no, this is really just the same Cartesian coordinate system that you're used to. The only difference is, instead of starting at the origin and locating points by x, y left and y, or x values left and right, y values up and down, you start from the origin and you go a certain r distance out radially, like the radius of a circle, and then you rotate through a certain angle theta. So, like if I wanted to locate the point, well, actually I want to draw on top of this, so let me know if there's a big glare on your camera. If I do this. Bad glare? No? So the way the coordinate system works is, instead of locating x comma y coordinates, you locate r comma theta coordinates. That's the two dimension, or the two variables used in the polar coordinate system. So if you see the way that these are set up, r represents the different radii of the circles coming out of the origin, like this. So on this particular grid of graph paper, you can scale it so that r equals 0 is the origin, r equals 10 is that last rung. And then if you look at the spokes that are going around, they represent different values of theta. And you've broken 90 degrees into 1, 2, 3, 4, 5, 6 equal parts. So each of these represent 15-degree increments, or what's 15 is 30 and a half, so Pi over 6 in half is pi over 12. So that's 15-degree increments, or pi over 12 if you're looking at radian measures. So if I want to locate the point r theta equals, I don't know, 6 comma 150 degrees. Okay, so it's a brand new coordinate system, but it still locates points two-dimensionally, just in a whole different way. You go to the r equals 6 rung, and then rotate around to wherever the 150 degree spoke is. So again, since these are 15 degrees off kilter, this is 180 right here. This is 15 degrees shy of that, 165. And so this is your 150 degree spoke position. So the coordinate r equals 6 would rotate around on that same circle until you get to that particular spoke. So that's the coordinate 6 comma 150 degrees. Or, again, you can interchange with radians. That's also 6 comma, what would that be, 5 pi over 6. Two different ways of representing the same coordinate. So it's still a two-dimensional coordinate system. But unlike x's and y's, every xy coordinate that you locate in the xy grid, for example, if you're plotting the point 7 comma negative 2, you go 7 clicks right, you go 2 clicks down. Is there any other way to label that coordinate in the xy coordinate system? Is there any other way for me to locate that same point without calling it x equals 7 and y equals negative 2? No. Still using xy coordinates. So if I'm in the xy coordinate system, that's a unique representation. There's only one way to represent all the points in the xy grid. Okay? But if you're in r theta coordinates, this point has an infinite number of representations. Okay? I mean, you can start over here at theta equals 0, go counterclockwise, like you do in trig, to 150 degrees and locate that point. You can also, and not just degrees and radians, I mean, that's technically the same thing. Calling that 150 versus 5 pi over 6 is really two different ways of labeling. Or the same way of labeling that point. If you go clockwise instead, and you get to that point, that's still r equals 6, but what's your angle become? 180 plus 30.
Yeah, 30.
And you're negative because you're going clockwise. So r equals 6, theta equals negative 210 is another way of locating that same point, because a negative angle starts over here on the positive x-axis, or the positive side over here, and rotates clockwise to locate that angle position. So that's two different ways of locating that point. Now, the weird thing about polar coordinates is you can also use negative values of r. And this is a little bit less than obvious. In order to use a negative value of r, you have to use the angle that's on the polar opposite side of the origin. Okay? So in other words, if I say r equals negative 6, but I still want to locate that point that's over here on the 150 spoke, I could go over here to where the angle is 330 or negative 30 degrees. And the point negative 6 comma 330 degrees locates that same point, because whenever you see a negative value of r, you go to the angle. If I go to the angle 330, I'm on this spoke. But if r equals negative 6, I can't plot it here. Negative values go through the origin and plot on the polar opposite side. So that's one of the weird things about polar coordinates, is you can actually use negative coordinates for r. Same thing with this value of theta. If I'm at negative 30 for theta, you're anticipating putting your point somewhere on that spoke, but if the r value goes negative, you go through the origin to the polar opposite side, and you actually have to plot the 6 value on that spoke on 180 degrees apart.
So negative 30, negative 6 be back at that same point?
So negative 6 for r, negative 30 will be another. There's 4 different representations at the same point. Okay, so just to make sure this hits pretty solidly, give me one representation of that point using a positive 10 value for r.
R comma 90.
Yep, there's the straightforward one, because it's on the 90-degree position. Okay, so we've eliminated the obvious one.
Negative.
Give me one that uses a negative value of
Negative
theta.
10, 270.
A negative theta.
Negative.
A positive r, but a negative theta.
Negative 90.
You
Or R
negative
negative
270.
10,
10, negative 270.
negative 270.
I want a positive value of r and a
Positive
negative
10,
value of
10,
theta.
negative 270.
Positive 10.
So positive 10, 270,
Sure.
270 is down here.
Negative.
Negative 270, yeah. Okay, so now you've been trying to give it to me. What's it? Well, this is a negative value of r.
Negative 10, 90.
Negative 10 and negative 90, because negative 90 would put you down here,
And then
negative 10 for r, polar opposite side. So see, unlike xy coordinates, polar coordinates have an infinite number of representations. Okay, that can be kind of a bit of a tricky thing. Yes?
Can you do 10, 450?
10, 450, yeah, because you can go outside the 0 to 360 comfort zone. An extra 90 beyond 360 puts you at 450. Yeah, so positive 10, 450 checks out as well. Positive 10, 5 pi over 2, same thing. Okay, so that's the rough idea behind the polar coordinate system. There are some conversions. Well, I guess I still need to overlap my graphing with this. Because anytime you transform from one coordinate system like xy coordinates into r theta coordinates, you got to be able to translate how the points are located and how they transform. So let me color code this in red versus, is that purple? Is it blue? Let's use black. Yeah, that's good. Okay.
Somebody else want to use it?
So I'm going to use black for xy coordinates, and I'm going to use red for r theta coordinates. Okay, so if I want to locate this point right here, I'm just picking a point at random. Okay, if I locate that point with xy coordinates, you go from the origin so far to the right for x, then you make a right angle turn going up, and that's why they're called rectangular coordinates, because you locate x's and y's going left, right for x, and then up and down for y. Okay, now the way you think polarly, polar coordinates are located by going to a certain value of r and then rotating through a value of theta. So this distance right here is your r, and this angle that you span through is your theta. And I forgot to label, this distance is your x, and this vertical distance is your y. So there's an inherent trigonometric relationship that exists between x's, y's, and r's and thetas. If you remember your trigonometry, which you should, according to the way the Pythagorean theorem works, since this is x as a leg of a right triangle and y represents another leg of a right triangle, one relationship that exists between these coordinate systems is x squared plus y squared equals what in terms of polar?
R squared.
R squared, because r represents the hypotenuse of that right triangle. So there is a Pythagorean relationship that exists between the x's and y's and the r's. Okay. What's another relationship? That's how you can link the polar r to the rectangular x and y. What's a trigonometric relationship that links theta with y and x? You got to use a trig function in that case.
X is r cosine theta.
No, you're giving me the opposite.
Oh.
I want to link x and y together to theta. Tangent.
Yeah.
The tangent ratio for theta is opposite y over adjacent x. So another conversion formula is if you do tan theta, that equals y over x. Oops, I shifted my picture. Not too bad. All right, good deal. So there's a couple of conversions that links x, y coordinates. You know, r is playing the role of the hypotenuse, where x and y were playing the role of the legs. Theta, that if you look at that as a right triangle, the y coordinate's always opposite, the x coordinate's adjacent. So the tangent ratio for any of these polar angles is y divided by x. Now, Nick, you gave me something else.
It's really just splitting up tan.
Yeah, if you split up tangent, or if you think of r as the magnitude of a vector, and if you think of x as the I component and y as the j component, how do you project the magnitude of the vector onto its I component using the angle theta? The magnitude gets projected down here using what trig function? Cosine. Or just go back to SOHCAHTOA. You know, cosine of theta is x over r. So if you solve that for r, or correction, if you solve that for x, x is the same thing as doing r times cosine theta. Because see, if you solve this for cosine, you get x adjacent divided by r hypotenuse, and that's consistent with trigonometric SOHCAHTOA cosine. Same thing for y. How would y split up using r and theta?
Cosine theta.
Yeah, y is playing the role of opposite of theta, r is hypotenuse, so y becomes r times the sine of theta. And these are collectively known as your polar to rectangular conversion formulas. Specifically, this is when you know polar and you want to get rectangular from it, because if you know polar, you know r and theta. So if you know your r, you know your theta, you can do these calculations to translate them to x and y. So this is really called polar to rectangular. This one is if you know x and y, you can get the r in one calculation. If you know x and y here, doing inverse tangent will tell you the theta in that calculation. So these take you from rectangular to polar. But they're kind of all used interchangeably when you see double integrals using polar coordinates. Now, here's one of the perks of polar coordinates. What's the graph of this equation going to give me? In 2D, in 2 dimensions.
Circle.
X squared plus y squared equals 9.
Circle of radius 9.
Circle of radius
So it's
3. Yeah,
Right,
centered
that's
at the origin. And it comes directly from that conversion. Yeah, x squared plus y squared equals 9. Notice what it translates to when you go to polar. Anytime you see x squared plus y squared, you immediately can make that polar conversion. X squared plus y squared equals 9 becomes the polar equation r squared equals 9, which can simplify even further. Something you can do here that you really were tempted to do there is take the square root of both sides. You don't have to. But here you can take the square root of both sides and get r equals 3. So circular equations become really, really, really easy whenever you're dealing with the polar coordinate system. Okay? As a matter of fact, any equation, 2 dimensions or even surfaces in 3 dimensions become easier whenever you see that expression pop up. For example, something you've done in 3D. Probably on your first test, when you were first dealing with vertical traces, horizontal traces, remember doing that? Maybe? Possibly? All the oids, the hyperboloids, the paraboloids, the, one sheet, 2 sheet, things like that.
Just kind of show the picture. I saw your video on that where you went through like a whole class of drawing them and everything.
Yeah.
We just went over a couple pictures.
Oh gosh, I love that section
Yeah.
because all the cool pictures you
It was
you
fun.
do get to draw. So y'all didn't get as intense with it as I guess I would have in my class. Okay, but here's the main thing you need to be able to do for polar. I mean, if you don't recognize this surface, it's okay. Its xz trace would be a parabola, z equals x squared in the xz plane. Its yz trace would be another parabola, so you kind of have this bowl shape out in space, a paraboloid. But notice what its equation becomes when you convert it to polar. Any use of x squared plus y squared can be used in 3 dimensions also. You turn that into z equals r squared, and then it's a polar defined paraboloid. Still produces the same points, still produces the same surface. Just sometimes any equation that uses x squared and y squared like this gets converted pretty easily to polar like that. What about one like this? What does that look like in rectangular coordinates?
Starts at 2.
Okay, it has an x and it has a y-intercept at 2.
Circle of radius 2.
Yeah. It's another version of a circle equation. You have a y-intercept at 2 because let x go to 0. Your x-intercepts, this would go to 0 when x was positive or negative 2. So the other thing to do is just to square both sides and bring the x squared over, and you can eventually turn it into this. X squared plus y squared equals 4. But what's the difference in this graph versus this graph?
That can be
Only
negative,
half.
that can't.
Yeah, this can use positive and negative y values. This can only put out positive y values. So this is specifically a circle of radius 2 in the positive y direction, or more properly said, a semicircle of radius 2. Starting here, semicircle stopping there. Now, this equation in polar, it still stemmed from this. You would still use r equals 2, but you'd have to state certain theta values that only produce that part of the curve. What theta values would give me that portion of the circle?
0 to pi.
Yeah, 0 to 180 or 0 to pi. Yeah. So for 0 less than or equal to theta less than or equal to pi, that domain restriction for theta for that curve would give me that upper half of the semicircle, radius 2. Okay. Now, let me see if we can sort of use what we've got and translate this into double integral information. Okay. When I first brought up the context of double integrals last week, we talked about, here's our domain, the xy plane. Now we're looking at it as our theta coordinates, using this as our underlying grid, as opposed to rectangular underlying grid with x's and y's, okay? And then there's a surface up here up above it. Maybe it's a paraboloid opening up. Maybe it's some kind of surface up here. We want to find that volume from here up to that surface using a double integral, okay? Well, you break the underlying regions into rectangles based on the way that coordinate system is defined. The underlying rectangles in xy coordinates are literally rectangles that are delta x units thick, delta y units thick, and then those became our dy dx differentials on the double integral as you integrate, okay? If you remember that first picture I had with the function and all the little prisms that come up to the surface, each underlying rectangle represents a breakdown of x and y like this. Well, the underlying regions here are not exactly proper rectangles. They got a couple of sides here that kind of go out at a pitch due to the angle theta, and then they have a couple of radial sides that are sort of, portions of a circular arc based on your values of r. So you can't exactly say that the area of this underlying rectangle is delta r times delta theta. Here, you can say the underlying rectangle here is delta x times delta y because they're rectangles. That's just length times width. So how do you get the underlying area when you have this sort of circle sector kind of chunk right there as your domain element? So this is where I want to go to the notes. So let me take my polar grid. And if y'all need some polar graph paper, I'll scan this in if you want this. I've got a couple of pages that have 2 per page, some that have a bigger one per page. It's so lame. I made this on Paint. It was just so easy. But Paint's just awesome. So doing double integrals in polar coordinates, okay? I don't want to skip over this because there's a little bit of, pretty important development here. And I don't want to insult you by reading it to you, but, I kind of need to get some points across. So if your underlying region R isn't exactly in the, the xy plane where you're used to using rectangles or even used to using lines and parabolas like the ones we did this past Tuesday, if you're integrating over circular regions or portions of circular regions, quarter circles, half circles, concentric circles like that, then anytime your domain of the double integral is circular or a portion of a circle, you're going to want to fall back on using a polar coordinate system for your double integral, okay? The conversion requires you to transform the dx dy in the rectangular integral to something else in terms of dr d theta. And unfortunately, it's not simply dx dy becomes directly dr d theta. All because, well, that's what your underlying rectangles look like. They're not proper parallel sides where you can use length times width to get the dx dy differential like we do in a regular double integral. You've got to figure out some kind of an area element for that. So here's what I want to go through this with you. Okay. Well, here's one thing that the easiest conversion to make is this. If you see x in the original double integral for rectangular, you can always replace x with, well, I wrote it on the piece of paper here a second ago. Yeah, you can always replace x with r cosine theta. You can replace y with r sine theta when you're converting from rectangular to polar. Or even this. The majority of the time you're going to be using this as your conversion. If you see x squared plus y squared in your original xy integral and you want to convert it to double in polar, then every use of x squared plus y squared becomes r squared when you translate it to polar. So you'll want to be using these conversions also. But the less than obvious conversion is what happens because of this. Since your underlying area is based on this chunk of a circular sector, what I'm doing is I'm fixing sort of a generic point right there, ideally in the center of each one of these little sectors that you're breaking the domain into, one of these little chunks of polar graph paper. And I'm recalling a formula from trig that you may have never seen before. The area of a sector of a circle depends on knowing the radius of the circle and the angle that spans the sector, 1/2 r squared theta. Okay? So I want to try to come up with an expression that gives me the area of this in terms of delta r and delta theta. Delta r is this distance because it's an increment of my r, my radius, coming away from the origin like that. This is delta theta because it represents, the distance between a couple of spokes on the polar graph paper. So I want to figure out how do these contribute to becoming dr and d theta in the polar double integral at the very end of the process. After you cause these things to shrink down as the number of rectangles approaches infinity and stuff like that. So if you want to analyze that area, I pick this coordinate that's sort of in the center of that polar rectangle. And if you look at this expression, it's giving me the area here is, let's see, r sub I plus half delta r going this way. And then that represents, well, yeah, that's right. R sub I is out here, plus half delta r. Okay, yeah. Okay, here's what you have to imagine. Imagine this coming all the way back down to the origin like this. Okay, all the way back to like a vanishing point. From the origin all the way out to here, that far is R sub I. But then I have to add an extra 1/2 delta r to get to the edge of that rectangle. So that full radius used in this calculation is 1/2 R sub I plus half delta r squared times delta theta. That would give me the area going all the way from here back to the origin of this little very, very skinny slice of pizza. But then I only want what's in gray there, so I need to subtract off the area coming from here all the way back to the origin. So I take my big skinny piece of pizza, and then I want to subtract 1/2 R sub I minus half delta r to there. So it tells me that's the radius times delta theta. So this is one arc length calculation going all the way out to the outer edge, minus another, well, arc length sector area calculation that isolates just what's in gray right there. Then if you go through the algebra ensues. I think I factored this as a difference of squares. I took out the 1/2 and the delta theta, and then this quantity squared minus this quantity squared is what's left over. So I did treat it as a difference of squares, and if you notice, the RI's cancel out here. Half delta R minus negative half delta R still stays, so that becomes a full delta R. And then in this other difference of squares split, Ri plus Ri is there, but then the half delta R's are what cancel. So it gives me 2Ri. So when this is finally multiplied together, you get 1/2 delta theta times delta R times 2Ri. But then the 2.5 cancel out, and that's what you're left with. R sub I times delta theta times delta R. What that means is if you were setting this up as a Riemann sum, you'd plug your coordinate here into the function f. That represents the height of your rectangular prism, if you can kind of see that coming off the domain like that. And then the base area represents this element I've got written in red over here. That's the underlying base, based on your base being sort of a portion of a circular sector. So when that translates to a double iterated sum, and you evaluate the limit as m and n both approach infinity, it turns into this. We started with this as our original double integral, just a double integral over the region R for f of x, y, dA, where dA is dx, dy, or dy, dx. But then through this conversion, you'll have to make polar conversions for the x's and the y's using polar conversion formula, so it becomes a function of r and theta. But then, notice it's not just dr d theta. There's this extra r that shows up as kind of like an integration compensator whenever you change from the xy coordinate system to the r theta coordinate system. So you still want to use all the conversion formulas that I mentioned earlier, but every time you convert from dx dy integration to dr d theta integration, there's always this extra r that you have to kind of put in there just because you're changing to a different coordinate system. Okay?
Does that R?
Because that comes from this. There's the extra r that comes out of the domain element, and see, this becomes the extra r that's in your double integral. This becomes the d theta. This becomes the dr. As your m and your n and the sigma double iteration approach infinity, your delta r and your delta theta shrink down to 0. But that still becomes your integration compensator. There's another name for this. It's also called an integration Jacobian, but that can go in one ear and out the other. I'm just calling it a compensator for switching to a new coordinate system. Okay. And you're going to ask me, did I completely interrupt your question?
What does that do anything?
Well, no. It's just the kind of the price you have to pay for converting to polar coordinates. So every time you're prompted to use polar integration, or you're wanting to change a relatively complicated xy integral into what seems to be an easier r and theta integral, that has to be included in the new integral you're creating, along with turning every x squared plus y squared into an r squared, along with turning every x, if need be, into r cosine theta, and turning every y, if need be, into r sine theta. So not just the coordinate conversions, but there's also this integration, double integral conversion that you have to go through too. But all it means is just put an extra r in there whenever you convert to dr d theta. Let's put an example to work. Imagine the nightmare of trying this with the integration we did this past Tuesday night. With dx and dy double integrals, you're committing to, if I do the dx direction first, I'm going left to right. Do I always have consistent entrance and exits for this whole region? Well, if that middle annulus wasn't there, that middle circle wasn't there as a void, yeah, I guess you could. You'd always enter on the left half of the circle, you'd exit on the right half of the circle, and then dy or dx wouldn't matter which order. But if you did do a dy dx integral, let's say you did do xy coordinates, what's the least number of double integrals it would take to integrate this function over this region? Well, consistent entrance and exits, if I choose the x direction first, 4. Yeah, it's going to take 4. Because I have this entrance and that exit here until I reach that inner circle's radius. Then I have this little patch right here, entrance and exits are the same. Then I have this patch right here, entrance and exits are the same. And then I have this lower portion where the entrance and exits are consistent. So you'd have to commit to 4 different double integrals if you stuck with xy coordinates. However, whenever you're doing a polar double integral, your coordinates don't work left to right, up and down like x's and y's. If you look back at that spider web piece of graph paper I've got, whenever you're doing polar coordinates, if you want to go in the r direction first, you don't just go left or right like you do x or bottom to top like you do y. R is usually considered starting at the origin. And which way does R go for its increasing direction? Yeah, but here's the cool thing. Omnidirectionally outward. You kind of have to think of R being like a big, radar blip, kind of getting bigger like that. So R goes from the origin outward like this in all directions. Ideally just in the direction of wherever your shape is, okay? And this one surrounds everything on the origin. So if you imagine R starting at the origin going outward, what would your limits of R be for this? See, if I just start at the origin and draw any radial ray going out like this, that tells me R goes from something to something else. What's the first thing R is always going to hit no matter which way I draw that red ray?
Pi over 2.
Yeah, square root of pi over 2. And the last thing R hits, yeah, no matter which way I go, because those are concentric circles, and circles work really well with polar coordinates. The square root of pi is your outer limit, okay? Then, unlike xy coordinates, you can't flatten this. See, in double integrals with rectangular, you can do the x direction and then flatten it to y, and it tells you the y limits. You still need to keep a fresh, robust, two-dimensional copy of this region because we've done our r limits. No matter which way I draw that radially outward, r always goes from here to here. Same limits. Now you want to do your theta limits. So beginning here at theta equals 0, what's the increasing direction for theta? Counterclockwise, just like from trig. So what values of theta, along with those values of r, span this full two-dimensional shape? 0 to 2 pi. If it's a full circular revolution, you're almost always going to have 0 to 2 pi for theta. What if we just have that? Well, sorry. There we go, that. Would our R limits change? No. If you're drawing through this gray region, R still goes from root pi over 2 to root pi in any direction. But theta goes from where to where?
0 to pi.
0 to pi. To 1 pi. 0 to pi. That's what you said. Okay, all right, I misheard that. What about that?
Pi over 2, 3 pi over 4.
The only thing that's going to change is theta. R still goes from root pi over 2 to root pi in any direction. Theta goes from pi over 2 to 3 pi over 2. Because that's 90 to 270. One thing you got to be careful about is theta always